Good morning, everybody. My name is Gabriele Bocchino. I'm a PhD student from Polytechnic di Milano, Italy. Working under supervision of Professor Ferrara, Liberato Ferrara, which some of you may know, I think. Okay, my presentation is understanding a fatigue behavior of high-performance fiber-reinforced concrete from the S-N curve to the Eurocode. So we are trying to take the European approach here. Okay, so as you know, and we saw a few wonderful examples just in presentation before, more and more structures are being constructed with FRC, going from deck bridge to pavements, industrial floors, airport, highway pavements, and more so are energy harvesting infrastructure, such as hybrid wind turbines, but also, and we saw as well a few examples during the convention, energy storage infrastructures. And by their natures, these kind of structures may be subjected to a number of load cycles during their fatigue life, from a few thousand up to millions or even billions in the case, for example, of energy harvesting infrastructures. Okay, so the problem of fatigue with FRC is quite relevant, and I think we should investigate, of course, the behavior under cyclic action. And also, for design, I think it's very important to have clear standards that can guide designers in approaching fatigue for FRC. And here I will go through a brief history of how FRC and fatigue have been treated in European standards. So starting with the Eurocode, the original version, we had no mention of FRC originally, and simplified methodology for fatigue, but only for ordinary reinforced concrete. Then we come to the Model Code 2010. Here we had classification of FRC and also design, static design. And regarding fatigue, again, here some explicit method with SN curves, but again, only for ordinary reinforced concrete. Now we come to Eurocode 2, which was recently updated. And now a new annex was introduced covering Annex L, but again, only the static action, and I will go deeper into the details in a few seconds. And again, fatigue, but only for ordinary concretes. Now Eurocode contains Annex E and Section 10, which deal with fatigue, but only ordinary reinforced concrete and compression only. And finally, the new version of the Model Code, again, builds upon the older version and also contains SN curve for tension, which is relevant for flexor. So the thing is that we have currently design rules and checks for static action, cyclic actions for ordinary reinforced concrete, but coming to FRC, there are no clear rules nowadays for cyclic actions, and this may hinder the possibility of using this material, which is very promising, as it has been shown, and is also it has enhanced capabilities, of course. So here, just a screenshot from Annex L, which was a great addition, again, to Eurocode 2, covering fiber-reinforced concrete. But probably due to a lack of sufficient experimental testing, there are no specific rules for fatigue on FRC. And the codes actually invite us to run tests. So this is what we started to do. We envisioned an experimental campaign. And the idea was to try to assess whether or not current formulations which were established for ordinary reinforced concrete are suitable for fiber reinforced concrete, and if not, what we can do about it. Okay, this is a schematic of the experimental campaign that we went through. We did this for compression and flexure, and today we will cover these two, but also for shear, material shear. We did Z-type push-off test. Okay, for each type of action, we did monotonic characterization to obtain static characteristic strengths, which allowed us to define load levels, which we used for defining load levels for cycling. We defined 4 upper load levels, 45%, 60, 80, and 90% with respect to the characteristic strength, for example, compressive strength for compression. And then we did test up to 100, 10,000, and 1 million cycles. For the test that did not fail during cyclic, we then proceeded to perform monotonic tests to obtain residual strength and try to assess the damage during cycles. Okay, so let's now delve into the monotonic characterization. We were provided with a material, an high-performance material from our partners at CEMEX. It is a patented material, so I cannot go too much into the details, but it is high-performance concrete with a hybrid fiber system, steel and synthetic fibers. So this is the characterization according to Eurocode 2. Basically, we obtain a characteristic compressive strength of more than 80 megapascal, which should correspond to 11,000 psi, and so a strength class of C80-95. We then did the same for flexure. So here we were interested into obtaining some key parameters. These are the limit of proportionality, and also the strengths at which are called FR1 and FR3 here in green and blue, which are the strength obtained for a crack mouth opening displacement, CMOD in short, of 0.5 millimeters and 2.5 millimeters. These two values are usually reference to for serviceability limit state and ultimate limit state. We then classified the material according to the classification that we can now find in Eurocode, which was loosely based on the one that we have also in model code. And basically, the classification entails one number, which gives us the strength class. And here we obtain a strength class in flexor of more than 8 megapascal. And then the letter gives us an indication of the post-cracking behavior of the material. Here with the letter C, this is a material, I would say, elastoplastic, slightly softening. Okay, so 8C class. Now, about the cyclic characterization. Again, we did 4-point bending test with pre-notch specimen. We did not did preload this time at a 3 Hertz loading frequency. Here you can also see a clip gauge to measure the opening displacement, the crack opening displacement. Again, for upper load level, a common lower load level, and the load levels were defined with respect to FR1K. So the residual, the flexural strength at crack mouth opening displacement of 0.5. So in total, 36 cyclic tests. And this is the typical curve that we can obtain. Initially, we preload the specimen up to the mid-level between the upper and lower load level. We then cycles up to the prescribed number of cycles. And then for the specimen that did not fail during the test, we unload them, and then we test them monotonically to obtain the residual strength, mainly FR1 and FR3. Okay, those are the results for 45% and 60% of the upper load level. In yellow, it doesn't show very well. You can see the results for 100 cycles, in blue 10,000, and in red 1 million cycles. And of course, as you can imagine, the larger is the load level, and the larger is the number of cycles performed, the larger is the accumulated crack mouth opening displacement. And this is the same for load levels 0.8 and 0.9. Here you can actually also see some X marks. Those correspond to premature failure of the specimen. In fact, for these load levels, we are not able to reach 1 million cycles. Again, this is a comparison of all the previous plots. As I was remarking before, the larger the load level and the number of cycles, the larger the CMODs, because we accumulate more damage, of course. On the basis of the results that I just showed, we obtained these plots relating the residual strength that were obtained monotonically after the cycles and the number of cycles. Of course, we would expect that as the number of cycles increase, the residual strength decreases. For load level 0.45, actually due to experimental scatter, which it is really something that happens for fiber-reinforced concretes, can be quite large, we even see a slight increase. So this is not physically just experimental scatter. For 60% of the characteristic strength, we can start to see a decrease. And finally, we see a dramatic decrease for 80 and 90%. Of course, because those were the specimens that did not reach 1 million cycles and failed. And so we consider the residual strength to be 0. On the basis of this, we were able to obtain these plots relating the residual, which is the counterpart of the damage, with respect to the performed number of cycles. And I point you to the definition of damage that we used with respect to the residual strength that we measured, FR1, with respect to the average residual strength that was measured during the monotonic test. And on the table here, you can see the obtained fatigue life that we obtained by interpolation for the one that failed, and by prediction for the specimen that did not fail, so mainly for 0.6. 0.44, since we didn't see any decrease in strength, as I was mentioning before, and this might be a limitation of this methodology, we are not able to estimate the fatigue life, but for sure we can say that it will be larger than the one obtained for the larger load level. Okay, so on the basis of these results, we then plotted them on an SN curve. The diamonds here are the predicted fatigue life number that were obtained previously, and the crosses are the experimental points for the test that failed, and this is the SN curve that we obtained. And again, here the load level is defined as the upper applied stress level with respect to FR1K. Now I wanted to compare this with respect to what we can find in the codes. As I was mentioning before, for the tensile behavior, which is what's relevant here in Flexure, currently the Eurocode does not have any formula. But what we can try to do is compare them with what we can find in the model code for ordinary reinforced concrete under Flexure. And here they employ a similar shape for the SN curve, of course, a different coefficient, but the important part here is that they employ a different load level definition, which is defined with respect to FCTK mean, which is the tensile strength of concrete, which made sense, of course, for reinforced concrete, because you know it's very brittle under tension, but maybe we can think of something else for fiber reinforced concrete. Again, this is the same curve without considering the load amplification factor and the safety coefficient. And here in green, again, same definition of the model code, but using our definition of the load level based on FR1. Again, here I'm not suggesting that we have to take out safety coefficients or load amplification factor, not at all. But what I think is that there is quite a margin of improvement, and as was suggested by many presenters during the convention, we really should aim at taking full advantage with the goal of sustainability, take full advantage of the improved capabilities of the material. So, as it was previously mentioned by some of my co-authors, FR1 may not be the most correct damage indicator, so we did the same for FR3. So I will go very quickly through these. Same residual versus number of cycle. In this case, for 60 and 45% of the load level, we obtain slightly better results, obtaining predicted fatigue life of more than 10 million cycles. And here the SN curves, very similar to before, slightly better. And again, we can see there is quite a large gap between what's currently in the code and what we obtain experimentally. Now I will present you the same thing, but for compression. Again, very similar kind of experimental procedure for load levels. This time, of course, we measure the vertical displacement to obtain the strain. And here, the residual versus number of load cycles. For 80 and 90%, we obtain between 10 and 40,000 number of cycles for the fatigue life, and about 1 million cycles, 2 million cycles for 60 and 45%. And again here, the damage variable is very important to look at. The damage variable is defined with respect to the average compressive strength. And these are the this is the experimental curve that we obtain, where we define the load level with respect to the characteristic strength. And here, the comparison with what's currently in Eurocode 2, the updated version. Okay, this formula can seem quite complex, but actually it's not very different from the one above, except that we have a term at the denominator taking into account also the ratio between the upper and lower load level. And the load level definitions that are adopted in the Eurocode. In the Eurocode, you will find a particular parameter, which is the FCD FAT, which is the characteristic compressive strength in design for fatigue. Here, I made explicit the definition of FCD FAT to better compare them, and basically it still refers to FCK. And again, in green, the same formulation using in the current Eurocode 2, but using our definition of the load level. And again, what I would like to stress here, that there is quite a large gap between what we found experimentally and what is currently in the design code. And again, we should probably try to find a way to optimize the design of fiber-reinforced concrete even in fatigue. So this concludes my presentation. Just to recap, we aim at starting to have an experimental database for fatigue of the fatigue behavior of fiber-reinforced concrete. And what we found is that probably there is the need to update or revise current formulation to take full advantage of fiber-reinforced concrete. And of course, in future work, we also invite other researchers, and I know that many of you are already doing this, to run supplementary tests. We should, of course, corroborate these preliminary results. On our part, we also started to investigate the role of pre-cracking as well as the role of loading frequency. And of course, investigate other damage indicators. For example, now we are trying to assess the damage based on the accumulated crack mouth opening displacement, you can see on the right, or its rate of opening. Okay, this really concludes my presentation. I would like to thank our partner at CEMEX. I would like to thank you all for your attention, and also ACI for awarding me one of the travel stipends, which allowed me to come here along my supervisor to this wonderful convention. Thank you, everybody.